Swayam Prabha. Digital India. Educated India. Swayam Prabha. Digital India. Educated India.
Let us have a look at precision approaches for landing. Landing is the most critical phase of an aircraft during its entire flight profile. It is said in aviation circles that takeoff is the second pleasure known to the man, the first pleasure is safe landing. So, to allow safe landing during situations when the weather is bad or to allow landing accurately at a destination airfield, precision approaches are normally used, and there are various types of methods available for providing a precision approach. First, let us understand what is meant by a precision approach. A precision approach by definition is an approved descent procedure using a navigation facility aligned with the runway where the glide slope information is provided. So, if you get information regarding the glide slope or the angle at which the aircraft is gliding and landing during the approach, then the approach is called as a precision approach. So, there are several types of instruments or instrumentation systems which are used for providing precision approach during landing. The most common and the most well known instrument system is called as the instrument landing system or ILS. There is also a more advanced version compared to ILS called as the microwave landing system or MLS. There is also a transponder landing system. Then there is a precision approach radar, and in modern times because of the growth of GPS, we also have ground based augmentation system called GBAS. We will look at all these precision instrument systems for landing, starting with the most common, the instrument landing system. So, the instrument landing system, which is normally abbreviated as ILS, it gives very high accurate and dependable means of navigating to a runway at landing. An ILS system provides two kinds of guidance, lateral and vertical. Going back to the history of ILS systems, it is not a new system. It was first proposed in late 1920s and system tests started in 1929. After testing it at various places and under various conditions, nearly 9 years later the first application of ILS was in 1938, way back, and in 1941 after extensive trials 6 systems were approved to be installed, and then slowly this became very common and popular all over the globe as one of the primary and the most commonly available precision landing system. This figure gives an overview of the ILS system and its various components, and let us look at all of them in detail one by one. So, the ILS system consists of 4 major components: three of which are shown in this figure, and the fourth one is the approach lighting system, about which we will talk later in some more detail. So, let us look at these components one by one and what their function is. First, we will look at the localizer transceiver, which is basically a combination of a transmitter and a receiver. So, this particular instrument is providing the horizontal azimuth or the horizontal guidance to the aircraft. So, it kind of localizes you and orients you towards the runway, so that you come in straight along the runway, and it is nothing but like a VOR system, very high frequency omni range system, but it is 4 times more sensitive and accurate. The next important component is the glide slope transceiver, which is again a transmitter and receiver. This provides vertical azimuth and it helps in automatic landing. This is working on an ultra high frequency. And then the third component is the markers. They provide the range information. Okay. Sometimes we locate them with a distance measuring equipment or DME, because both of them are instruments which give range. As you can see, there are generally 3 types of markers. The outer marker is located approximately 6 nautical miles or 11 kilometers from the runway end, shown here in the blue color. The middle marker is located half nautical mile or approximately 1 kilometer from the runway end, as shown in the amber color or the orange color here, and the inner marker, if it is there, is located around 60 meters or 100 feet from the edge of the runway. Sometimes this is omitted, because by the time you reach 100 feet from the runway, you are actually very near and you really do not have much time to take any corrective action. So, only in very accurate systems, high level systems, we have the inner marker, otherwise it is omitted in the low level systems, and we will see those details later under the categories of the ILS system. But before we define the categories, we need to understand the concept of runway visual range, commonly abbreviated as RVR. So, what is RVR? It is the maximum distance in the direction of takeoff or landing at which the runway or the specified light or markers delineating it can be seen from a height corresponding to the average eye level of pilots at touchdown. So, the value of RVR tells you what is the kind of visibility that the pilot will actually have when he or she touches down. So, RVR is generally measured at the eye level of the pilot, and either the end of the runway or some designated point at the runway. If it is you just check how much is the visibility to that point, and when you quote RVR 24, it means that the runway visual range is 2400 feet, and if you report R36/400 feet/D, it means that the RVR for runway 36 is 4000 feet and it is decreasing with time. How do you measure RVR? Earlier it used to be done by sending a person and he or she would just look and give an idea about the RVR, but that is unscientific method and it is subjective. These days we use an instrument called as the transmissometer, which is located along the side of the runway, and this essentially has a light source plus a photoelectric cell receiver. So, what it does is it senses the reduction in the light level as it travels. Such an instrument has a range of only 6000 feet, but that is good enough for landing, because seldom you will need to have a runway length more than 6000 feet to ensure sufficient visibility. RVR is normally measured at 2 locations, either at the 2 two locations. RVR is usually measured at two locations, the touchdown point where it is called alpha and at the midway point where it is called bravo. Another concept to be understood before we go to the categories of ILS systems is the decision height. This is a specified height during the precision approach at which a missed approach must be initiated if the required visual reference to continue the approach has not been acquired. So, as the pilot comes into land, when you reach the decision height or when you reach the point in space at which the altitude of the aircraft above the ground level is equal to decision height, you should be able to acquire the visual reference specified. Generally, it is the beginning of the runway, and if you do not get it or if you do not have the visual reference at that point, you are supposed to abort the landing and execute a missed approach. Now, what is a missed approach? In a missed approach, the aircraft comes into land, it attains a decision height and then decides not to land, but continue ahead by missing the approach. This is the missed approach. Right. Now, the decision height allows the pilot sufficient time to do three things: to safely reconfigure the aircraft to climb, to execute the missed approach procedures, and while doing it you avoid the terrains and obstacles. So, based on the values of the runway visual range and the decision height, there are various kinds of ILS categories. The categories are 1, 2, 3A, 3B and 3C. As you go down this table, the runway visual range will reduce and the decision height will also reduce. Category 1 system is the most basic system, in which the decision height is 200 feet or 60 meters. So, when the aircraft comes as low as 200 feet above the ground, there should be a visibility of 800 meters, or you should be able to acquire the runway at a distance of 550 meters. In category 2 ILS system, the decision height is reduced to 100 feet or 30 meters. So, you are further down in the flight path. At that point, the visibility should be at least 350 meters. Category 3A system, the decision height remains the same 30 meters, but the visibility is reduced from 350 to 200 meters. In category 3B systems, the decision height is further reduced to 15 meters or 50 feet from the runway, and the visibility at that point should be at least 50 meters. And finally, we have the category 3C system. In this particular system, which is the most accurate level of ILS, the decision height is 0 and the RVR is 0, which means you are allowed to execute a blind landing. The aircraft lands completely on its own with the help of onboard and ground based instruments. So, here is the table of all the ILS categories at one shot. As I mentioned, as you go down this table, you will see that the RVR values are reducing and the decision height is also reducing. So, now let us have a detailed look at the ILS components one by one. First, let us look at the localizer, which, as I mentioned, uses a VHF to give you the horizontal guidance. The localizer transmitter is basically an antenna array which is located beyond the departure end of the runway, and it consists of several pair of directional antennae. It transmits two co-located VHF signals, and globally the range of the frequency of the carrier frequency for the localizer is between 108 megahertz to 111.975 megahertz. At any airport in the world, you will find that the localizer is going to be tuned when you come into land at a specific frequency within this particular band. Now, as I mentioned, there are two signals which are transmitted. On the carrier frequency, we have two signals. One is at 90 hertz, the other at 150 hertz, right. And each antenna transmits a narrow beam on both sides of the runway with an overlap. The beam width is around 5 degrees, and therefore, as you go for the distance it increases. At the runway threshold it is about 700 feet, and when you go to 1 mile it becomes 10 nautical miles. So, 10 nautical miles away from the aircraft you have the width of 1 mile, and at the runway threshold, which is the aim point for landing, the beam width is around 700 feet. So, your aircraft can be laterally aligned. This is a picture of a localizer antenna or a sketch of a localizer antenna. Once again, we will record this again. This is the sketch of a typical localizer antenna. As you can see, these are series of antennae which are mounted parallel to each other, and here is a photograph of one such localizer antenna array mounted at KMEZ airport, runway 27 at a place called Mena in Arkansas, USA. So, you will notice that each end of the runway will require these series of localizer antennae if you want to have ILS along that path. Now, we look at the receiver. Receiver is the onboard equipment mounted on the aircraft. It is usually paired with the VOR receiver that you have on the aircraft, and it basically measures the difference in the depth of modulation of the two signals mounted on the carrier frequency. So, the DDM value depends upon the position of the approaching aircraft from the center line, right. When DDM is equal to 0, that means you are perfectly aligned with the center line, and that is what is desired. Then you can use the horizontal situation indicator or the course deviation indicator mounted on the aircraft to show any offsets. Okay. And the reception range of a localizer receiver is around 18 nautical miles if you are within a 10-degree track, and if you are within a 35-degree track it is 10 nautical miles. So, 10 nautical miles is also the range at which you can get the signals. Moving on, let us look at the glide path. The glide path is using a ultra high frequency component, and that provides the vertical guidance. It is called as a glide slope path antenna. This is a ground based UHF transceiver and airborne receiver. So, the frequency at all airports is between 329.3 megahertz and 335 megahertz. It is a very small frequency band, and generally the aircraft are supposed to come at a glide slope of around 3 degrees. This number can vary based on the terrain and other obstacles. This number can vary little bit more or less than 3 degrees based on the terrain and the other obstacles present at the runway, but generally it is around 3 degrees as the mean, and you monitor it to plus minus half a degree accuracy. Okay. So, the instrument per se is situated on one side of the runway touchdown zone. Okay. As we saw in the previous images, it is on one side of the runway, and the offset could be about 400 to 600 feet from the center line and around 750 to 1250 feet down the runway from the threshold. So, the localizer and the glide slope frequencies are generally paired. So, therefore, only one selection is required to tune both the receivers. So, the glide slope path signal like that of the localizer are again two overlapping beams. Again they are modulated at 90 and 150 hertz like the localizer. They are radiated primarily along the approach track where the aircraft comes in, and the thickness of the approach of the overlap area will be 1.4 degrees. So, this will be just about 0.7 degrees above the optimum glide slope, but as you go far away they will become thicker because of the radiation. So, it will be 1500 feet thick at 10 nautical mile range, it will be 150 feet at 1 nautical mile range, and at touchdown the beam width will be less than 1 foot. So, that is the kind of accuracy you can get. Moving ahead, we have the third component called as the marker beacons. These are used to provide the information from the distance from the runway. Okay. And along the approach path there are some predetermined points at which these are installed. So, when a pilot is approaching an airport, they already have an idea about the location of these markers at a specific airport. So, they get a situational awareness of where they are. Okay. So, this is normally done using low power transmitters operating on 75 megahertz. They radially elliptical beam, they radiate an elliptical beam upward from the ground. At the height of 1000 feet, this beam will be around 2400 feet long and 4200 feet wide. There are generally 3 markers: the outer marker, the middle marker and the inner marker. So, the location of the outer marker is approximately 6 nautical miles or 10 kilometers from the runway threshold. That is the final fix for non-precision approach. It intersects the glide slope at elevation of around 1400 feet, and as the aircraft passes the outer marker, on the instrument in the aircraft you will have a blue colored light flickering, and there will be also an aural signal. Generally this is co-located with DME if possible, because it will also give you a distance, and sometimes it is replaced by a non-directional beacon, which is a less accurate system. The middle marker is located approximately 1 kilometer or 0.6 nautical miles from the threshold on the extended runway center line. It crosses the glide slope at around 250 feet above the runway elevation, and as the aircraft passes the middle marker, an amber light and an aural signal of a different type is played. So, the pilot is getting a clear indication that you are now above the middle marker, and generally the location of the middle marker is near the missed approach point for the ILS Cat-1 approach. The inner marker is located approximately 100 feet or 60 meters from the runway threshold. This indicates the imminence of arrival of the aircraft at the runway threshold in low visibility conditions. And inner marker, as I mentioned, is omitted on low category ILS systems. It is installed only in category 2 and category 3 systems, because the position of the aircraft as it reaches the Cat 2 minima is roughly at the inner marker. So, in the cockpit there is an indicator which will flash a white colored lamp in unison with an audio warning of a higher frequency as we cross over the inner marker. So, the working of the ILS system is best illustrated using this particular video. So, you will see in this video an aircraft approaching from the top left side, coming into land, and we will see what happens to the aircraft, and also we will look at the instrument in the cockpit. Okay, so, here we go. So, you can see the aircraft is approaching. Right now it is above the glide slope. Okay, it is the yellow line is the correct glide slope. So, let us have a look at what kind of indication the pilot gets in the cockpit. So, at the moment you are correctly on the glide slope. So, but if you are deviating, if the nose is towards the starboard side, you can see. So, the pilot basically just tries to bring the crosses align. Here it is going a bit to the left, and now it is perfectly aligned, and those are the 3 beacon audio warnings. So, you can see in the bottom that the aircraft is just about to fly or reach the outer marker, and as it reaches the outer marker you will see the lights flashing and aural warning. So, that is the blue light and the outer marker audio signal that comes in. Okay, so now the pilot has almost correctly inclined the aircraft, maybe slight problem. The illustration here is just to show how, if the aircraft is not exactly aligned, how does it look in the cockpit instruments. So, you just have to ensure that the crosshairs are matching with the dotted lines in the cockpit instrument. Now, approaching the middle marker, watch out. Okay. Once you have crossed the middle marker, you are now going to look, you are now going to approach towards the inner marker. So, inner marker is, as I said, very near to the runway, just about 60 meters from the runway. And that is it. So, at the end of it, you are landing on the aircraft. Okay. So, the three systems we saw, the glide slope, localizer and the markers were the three main components of an ILS system. Another important component is the approach lighting system. So, this is the lighting system on the runway approach end, which extends outward from the runway end, so that the pilot can see visually how well aligned the pilot is with the runway before landing. It consists of a series of lights. Okay. There are light bars and there are strobe lights, or there is a combination. This is provided in all instrument approach procedures. It allows the pilot to visually identify the runway environment once it arrives at a prescribed point on an approach. And the approach lighting system can be operated either by the air traffic controller on the ground, or there are certain situations or scenarios in which it can also be operated remotely by the pilot, as we will see. So, let us look at some typical approach lighting systems for various categories of ILS. So, for category 1, here is a picture of a simple approach lighting system. So, there are two components here. There is some components which are on the runway, and there are some components which are elevated and they are in the approach path. So, the ones below the green line is the runway touchdown target point. Below this is what you will see beyond the runway, and there will be some elevation, they will be at some height, and what you see above this in this figure is the runway. And on the left and the right hand side, you can see there are 4 lights each, and this constitutes what is called as the precision approach path indicator, abbreviated as PAPI lighting system. So, this gives a visual indication to the pilot. If the pilot is flying below the glide slope, then you will see 3 red lights and 1. If you are very below, very much below, you will see all red lights. If you are above, slightly above, you will see 3 white lights and 1 red light, and if you are very much above, you will see all white lights. In category 2 systems, we illuminate the edges of the stopway, and also we give some yellow colored lights in the caution zone, and then you have multiple rows of lights in the approach path, and then there are these blue lights which are also indicative. Okay. And if you go further to the category 3C systems, you will see that the supplementary approach lights are indicated by red colored. The touchdown zone is illuminated with more lights. There is a center line, color coded line, and there are some threshold and warning lights. Okay. So, the lighting systems also differ depending on in which category the ILS system has been certified to operate. As I mentioned, it is possible to also remotely operate the approach lighting system by the pilot. This is normally called as the pilot controlled or pilot activated lighting, PCL or PAL. Here what you do is you use radio control, or you send a signal through a radio to control the aerodrome lighting. The pilot can communicate from the air to the ground on the radio and switch off either only the approach lights or the runway edge lights or the taxiway lights, or all of them depending on what the pilot needs. It generally has 3 settings. The first setting is low intensity, in which there will be 3 clicks in less than 7 seconds, medium intensity when you will have 5 clicks with less than 7 seconds, and you have high intensity where there will be 1 click every second. So, it will be 7 clicks in less than or equal to 7 seconds. This system automatically turns off 15 minutes after the touchdown of the aircraft. Now, let us look at some limitations of the ILS system. The first and the foremost, an ILS system makes the aircraft to come in a straight path along the landing. So, about 100 nautical miles or more beyond the airport, you have to align yourself with the runway center line, plus the angle at which you come is also constant, and it is the same for all the aircraft. Now, various aircraft types come in at the same angle at any particular runway having an ILS system. Then the 2 components, localizer and glide slope transceivers, they are very sensitive. Okay. Localizer is sensitive to the obstructions in the signal broadcast area, especially large hangars, buildings, they obstruct a lot, and the glide slope systems are very much sensitive to the terrain in front of the antenna. So, if you have uneven terrain in the glide slope, you will have multiple reflections. When you have multiple reflections, there will be uneven glide path prescribed by the instrument on the cockpit. So, it is not really very handy. Also, the ILS system is very expensive to set up, expensive to maintain and calibrate regularly. The sighting criteria or the criteria used for placing the system and the complexity of the is very high, and therefore, it requires a lot of investment and continuous expenditure. So, to fight or to counter the limitations, a system called as a microwave landing system was proposed many years ago, and it was supposed to replace ILS system after 2010. What is this? What is the benefit of MLS system? It uses wider selection of channels to avoid interference. Earlier I mentioned to you that there is a fixed and a small frequency band in which the localizer and glide slope antennae are transmitting. Here there is a much larger selection. Then it gives you excellent performance in all weather. It has a much smaller airport footprint. In the case of ILS, you need to install a large array at each end of the runway where you need to have landing, and plus you need to have the glide slope indicator once again at each end of the runway. Here you can manage with smaller footprint, right. It can give you wide vertical and horizontal capture angles, allowing approaches from wider areas around the airport, including curved approaches, but it was not successful. It did not gain popularity because of 2 things. One is that many airports had already installed systems, and it was very expensive to remove them and put something new. So, because of legacy, they had no motivation to remove and go for newer system. And also in recent times, there is an availability of GPS and wide area augmentation systems, and these allow you, as we will see, these allow you to come up with precision approaches with much lesser instruments. So, therefore, there is no interest now in replacing the ILS system with the MLS system. You can look at the coverage volumes of the MLS system. See, you can see that on both the sides there is a huge coverage volume, and therefore, it allows you to come in curved paths. Focusing on the azimuth coverage volume, you can see that up to plus minus 40 degrees at a range of 20 nautical miles, the MLS system can give the coverage, and this particular coverage can be further widened to about 60 degrees, but then the range will be reduced to around 14 nautical miles. And on the elevation side, whereas the ILS system gives you only around 3 degree, the coverage in the elevation in case of MLS is around 15 degrees, and it can be also further stretched to around 30 degrees. Another interesting system that is used for precision landing is the transponder landing system, or TLS. This came into being when it became more and more popular, and sometimes regulatory bodies insisted that every aircraft should have a data transponder. So, then why not query that data transponder to get its location and use that to provide the information. So, it is an all weather precision landing system for precision approach, which uses an existing airborne transponder and ILS equipment already available on the ground. It interrogates all transponders of the aircrafts within 100 nautical miles from where you are, and it determines the aircraft position using 3 antenna signals. One of them is used for the horizontal location, the other for vertical location, and the third for the trilateration, which gives you the ability to locate a fixed point in space. In case of TLS, real time guidance is provided on the radar scopes, which are similar to the secondary surveillance radars. A TLS system is used where the ILS or satellite based navigation is not possible or not reliable. For example, you could have very short runways where you will not be able to really have the land required for installing all the ILS components. You may have obstacles, you may have real estate constraints beyond the runway where you cannot install the approach lighting system or the various members, and there could be that on both sides or on one side you are approaching over water, over a sea or over lake, and then in that case it becomes difficult to install and maintain the systems. Also, satellite based navigation system also suffers from accuracy when you come near the Arctic Circle or the equator. So, if you have an airfield located near the Arctic Circle or equator, and if you do not want to use any ILS based navigation system, then you can use a TLS system. Then we look at a precision approach radar. The PAR is a radar system to provide lateral and vertical guidance to the aircraft at landing, and here there are some ground based controller or controllers. They will guide the aircraft till it reaches the decision height. After that, the option is left to the pilot to decide what to do. Okay. This is also called as a ground controlled approach, or GCA, because somebody on the ground is controlling you. The PAR has a unique radar display with 2 separate traces. The upper trace gives you the elevation and the lower trace gives you the azimuth guidance. As you can see in this particular photograph, we see that the face of one of the air traffic managers of the Air Force is flashing on the screen. It is not intentional, it just happens, but the 2 displays that you see one below the other are the ones which are unique and they are used to guide the aircraft. A PAR system is used mostly in military aviation, especially in the Navy, because they do not want to declare their position. Here is a photograph of a precision approach radars mounted in a German military airfield. And then finally, these days we are looking at what is called as a ground based augmentation system, or GBAS. GBAS is an all weather landing system which uses GPS data from the GNSS satellites, and these signals, they have a real time differential correction. So, the local reference receivers, they take the information and dump it on a central data server, and the correction messages are worked out, because what you do is you ask the GPS what is your location, and you already know your location. So, the difference between GPS prediction and your own observation is calculated, and that correction is sent to the aircraft using a VHF data link. So, then the pilot can correct the numbers and hope to have a more precise landing. There are various types. The one which is currently in use is called as the GBAS approach service type C, short form is GAST. In the GAST, We have currently cleared it for only Cat 1 minimum, we have not gone beyond that. In the future there is a system called like gas D which is expected. In gas D there will be a permission for touchdown with Cat 3 or 0 visibility, 0 decision height case with Cat 3 minima. And in the future there is a movement towards consolidation, so that a single ground based augmentation receiver, it can replace many navigational equipment such as the ones listed here. If you have an ILS, you have to put on each runway. You can use NDB VAR, you could use the microwave landing system, or you could use the GPS. Now, earlier the name of this system as per FAA was LAA, which stands for Local Area Augmentation System, but now under the European regulations or the ICAO, it is replaced by GBAS or Ground Based Augmentation System. So, here is an overview of the GBAS system, how GPS satellites are communicating the location of an aircraft and also the location of an existing GPS receiver or receivers as in this case, and then you calculate the error in the GPS if any based on the predicted value of these receivers against the known values, and then the correction is then transmitted to the aircraft, so that the aircraft pilot can inform everybody else that this is the kind of error which has crept in. Thank you for your attention.